times dy. dy is a cosine t. All of that dt. Negative a. Oh, I didn't put it. I know we said it, right? We did say it. That's a negative. And I'm going to get so many lashings for this. It's terrible. I appreciate y'all paying attention, though. I mean, these are little things or big things, right? Integral 0 to pi. What now? Yeah, look, I mean, so many great things happen here, right? This negative a squared cancels a squared. We get sine squared t. And the other one turns into cosine squared t dt, which is just integral from 0 to pi of 1 dt. And if you plug in, well, that's t evaluated 0 and 2 pi, and you just get 2 pi. There it is. That is not natural, right? That's not a natural thing to do. It's utilizing this, which seems completely disconnected from any, like this doesn't seem like that's going to help you get this, right? But it does. All right, so there will be a couple problems like that on the final.
Oh boy.
No, I'm kidding. That was more just to show like the power of thinking, I guess. All right, homework, we're done.
That was cool.
Yeah, it is. That is a really cool thing. I like to show it. What nerd came up with that?
Isn't that like a method in general? Like if you can prove for any value a, then it holds.
Yeah, I mean that's what mathematicians do. It's always about trying to generalize, right? It's always about trying to find the most general case where something holds true, right? Like we can have specific, like when you're in a physics class, you all will hear about something in physics called flux. Yes, or in engineering, you'll hear about something called flux. That's that's a very, in physics, we're usually restricted to very like specific shapes. Specific like cylinders or spheres or things like balls. But a mathematician would want to know, what about flux on anything? Like just arbitrary. Everything is always about generalizations, always. Like that problem we just did showed that for that vector field, now that vector field was important, wasn't it? Why was that vector field so important in that problem we just did? Do you think the vector field mattered? Absolutely, because when we did those partials, partial q with respect to x minus partial p with respect to y, what did we get? 0. And if that wouldn't have been 0, then we couldn't have moved that other integral to the other side. So it had that part there, that partial part, had to be 0 for that theorem to work. If you change the field, you're not guaranteed 2 pi anymore.
But there are an infinite number of fields that would.
Yeah, there's an infinite number of fields where that would happen, right? In fact, that would happen for any what? What is this being 0 means what?
Any curve around the origin.
So any curve that goes around the origin that encloses the origin, the work would be 2 pi if this is 0, which means these two have to be equal, which means
We're at this point.
which means
Gradient, something conservative.
conservative.
Oh, I got it.
Right? Because what is our check for conservative vector fields? That these two have to be equal, right? So if these two are equal, that's always 0, and therefore, generalizations, right? What we could say is this. If you give me a curve, C, positive orientation, as long as it encloses the origin, and as long as this field that I'm calculating the work on, as long as that field is conservative, then the work done is 2 pi. Done. You can draw any curve. That's how that works. All right, cool. Glad we got to that. In classes like this, sometimes I don't know how far y'all want to go down these rabbit holes, you know? You just missed something pretty good. Because you're more math major, right? We'll talk maybe after class, right? Don't you think? Okay.
Sorry.
It's a pretty big thing. Well, we weren't initially going to go down that road, but we did, and okay.
I had 2 drinks.
It's okay. It's okay.
It's okay.
All right, so we are in the next section. This section is actually a little bit of a relief because it's just some formulas, and there's some pretty cool geometry that goes with these ideas. And so it's very mechanical, and then we'll use these as we proceed. So we're going to talk about these 2 things called curl and divergence. And so we all understand kind of what a vector field is, right? I mean, we've been using them, right? It's some vector that each component has a function, right? And you have these vectors all over the place, right? And you're either in 2-dimensional space or 3-dimensional space. And those vectors could represent gravity or electromagnetic, like a field of magnetism, something like that, right? It could be a lot of things. Flowing water, what direction the molecules are wanting to go, how fast they're wanting to go that direction. So vector fields in general are pretty general. We're going to define 2 operations with vector fields. These are things that we can do to vector fields to create something new. So the first one is called curl, and the second one is called the divergence of a vector field. So given a vector field F, we now define curl and divergence as follows. First, curl. The curl of a vector field is you take the vector field F, which has the component functions P, Q, R, and by definition, this is notation, curl F is this quantity right here. That's it. And when you look at it initially, you're like, whoa, that looks nuts. But all it is this. The curl F is just this right here. And that's going to look really weird when you first see it because you're like, wait a minute, hold on. What's this?
Del.
That's del. So it's been the del symbol, right? But haven't we been using that for the gradient of F? Right? What's that? Yeah, there's 2 dels. You also can call that del as well. People like complain, math people complain a lot about the fact that it means the same word for 2 different things.
Is that del crossed with F?
This means del crossed with F. Okay, this should be weird. Remember what cross product means, right? If I gave you 2 vectors, if I said take the vector 1, 2, 3, and cross it with the vector 5, -1, 4. We all know how to do this, right? Do the cross product. I usually would line them up like this. I like to put the other vector below it like this. And then we're going to get a new vector. When we cross these, it'll be the determinant here, right? And then minus the determinant there is the middle one, then determinant last time, right? That's how we do cross products. Whenever we do cross products, though, it's a vector, right, with a vector. I'm asking you to cross what with this is a vector, but what's del? It means take partials, right? So this is the first time we've ever seen del used like this. We're going to, when we write del by itself like this, what we mean is it's what we call a partial operator. What it's going to do is it's going to be a vector. This is going to be a vector. It's going to be the partial with respect to x, partial with respect to y, partial with respect to z. That's the vector. It's actually really a vector that is an order of instructions. It's saying you're going to do the partial with respect to x, partial with respect to y, partial with respect to z. And you're going to do that on the field P, Q, R. All right? Let's write this like I just did those vectors there for a second. Or I did this, right? I did partial with respect to x, partial with respect to y, partial with respect to z. And I put this vector underneath it, P, Q, R. And now let's do the cross product. So our answer here, what's the first component? Well, we cover up this, right? We cover up this. And normally this means multiplication, doesn't it? Like this times this minus this times this. It's no longer multiplication, it's an operation. It's the partial of r with respect to y, okay, minus, or, yes. Does that make sense to you? Let me get to the notes. Where am I? I'm going to do it right there. Let me move this down so you can see that. So without us actually having to go through the whole thing, right? If I cover this up, partial of r with respect to y minus partial of q with respect to z. That's the first one, right? And then the next one, cover up the middle, and we do the opposite, the negative of this. So partial of r with respect to x minus partial of p with respect to z, but then change the signs. And that gives you the middle one. And then the last one. Yes or no? Yes? Y'all good with that? Pretty cool, right? I mean, it's the first time we've ever seen anything like that. So we have a special name for this. The del by itself is this vector. And it's called a differential operator. So it's basically an operation. It's something that does the operation of differentiation for us. What else do I want to say here? Does anyone recognize anything in that formula at all? Do y'all recognize in that formula, do you see anything you've seen before? The what? The what? Yeah, no, not here. Look in there. Do you see anything? Recognize anything? Wasn't that in Green's theorem? Right? Wasn't that in Green's theorem? What did we have to check to say something was conservative? That these were zero, right? That basically these were equal. So something is connected here to stuff we've seen, right? And that's what we see in Green's theorem, and that's the check for conservative. So something interesting.
How do people come up with that? What kind of deal with a devil do they make?
You know, what's interesting is, I think is interesting is that nobody is coming up with anything, right? We are just discovering what is, right? Like it's not a matter of, like we put the structure in place, right? We create the real number system. We have our axioms that basically the do's and don'ts of our system, and from that is born the mathematics, right? It's not like we said, let's go make this theorem. It's that theorem is there, right? It was there. There are theorems out there right now, right, that we haven't found. They're truths that we just haven't discovered yet. That makes sense? So it's kind of a weird thing, right? It is a philosophical debate. Yeah, it is a philosophical debate. Really? That'd be an interesting conversation for sure. Compute the curl. Yep. We want to. Hey, this is better than the other stuff. I think this is a lot easier to do. So I'm going to compute the curl of this vector field. So what I'm going to do is I'm going to take the del operator, instead of memorizing the formula, just do the cross product because we've done them before. Okay, I'm about to do the cross product of those two things. All right. It's going to be a vector, right? We're going to get a vector as an answer. So cover up this. Okay, here we go. Partial with respect to y of this. What's partial of that with respect to y? Xz squared. Okay, xz squared minus. Now, this and this together. So I'm doing the partial with respect to z of that middle piece. Xy squared. Y'all got that? Any questions on what I did there? It's not multiplication, right? It's an operation you're doing. Now, cover up the middle one. And do y'all want to just do what we've done in the past, put a negative there and then do it? Is that all right? Okay, so here, partial with respect to x of this. yz squared. And then this one, x squared y. And then we'll have to distribute a negative through there. Are you all following me? Yes? Y squared z minus x squared z. Boom, that's the curl. The curl is a new vector, isn't it? It's a new vector. Yeah, so now the next thing I'm asking is to find the curl. All right, we found the curl of the vector field. Now I'd like to know what the curl of that vector field is at 2, 1, 0. So at the point 2, 1, 0, we get the curl to be a vector. Let's see, I'm replacing z, right, x, y, z. So 0, I think we got negative 2 there. 0. Y'all getting 4? 4, and then 0. Pardon? Oh. And then 0 for the last one because they both have z's. That's the curl. It's a vector. Yes?
Is this like the curve that we learned at the very beginning of the semester?
The curve that we...
The curve from the, yeah.
It's not the curvature. Okay, I'm going to show you what it is because curl is really awesome when you understand what it is geometrically. I just wanted to make sure we get the formula and we understand what, like, how to compute it. Did you have a question? No.
Is there a symbol for curl, or do you say curl?
Curl F, yeah. Curl F. Yeah, I mean, you just... There. Yeah. Yes? You could also cross, sorry, cross. That would, if you wanted to, like, more of a symbolic, del cross F is curl. All right, so we start out with a vector field, right? We've got this vector field. Let's for a moment imagine that this vector field represents like water. Let's say we have this big container of water. We're in the middle of the ocean, right? And each molecule of water is moving in some direction. And that direction it's moving at a certain velocity as well, right? So for every molecule of water, you have this vector. The longer it is, the faster it's moving in that direction, right? And then, of course, the arrow points in the direction it's moving. What is the curl? Well, at that point, in this particular case, this vector field, at that point, the curl is a new vector. So we have one vector, which is showing which way the molecule is moving, right? That's the field vector. The curl is another vector somewhere here. And the question is, what is it, right? What does that vector represent? You ready to see it? Okay. Oh, let me erase this first. I have another example with a two-dimensional vector field, but let's just get right to the animation of it. This was one of the hardest things I've ever had to code up, this right here.
How long did it take?
Well, a lot of the code was easy. I'll show you this. Let me show you what happens here first. Okay, so what you're seeing here is three-dimensional space, all right? And imagine here that you've got that molecule of water, all right? The red vector, if I remember correctly, yeah, the red vector is the direction that the molecule is moving, all right? So this red vector, this molecule of water is moving in that direction, or you could say that's gravitational force, or you could say it's electromagnetic force, okay? We're gonna stick with water because it's easier to understand. So this molecule of water wants to move in the direction of that red vector, all right? So as it's moving in that direction, it has a curl to it too. So the things around it are actually affecting it. So as it heads in that direction, it's the things around it, think about it like brushing up against the side of it, and it's causing this to actually rotate as it moves. That's good animation, right? So look, this right here, this green vector is the direction of the spin. All right, so we've got this molecule. It's wanting to move in this direction, right? I said that wrong. The molecules want to move in the direction of the red vector. The green vector is the axis of rotation of the spinning of the molecule. So the green vector creates an axis of rotation, and then the magnitude of that vector is how fast it's spinning. So can you imagine this molecule of water? It's moving in this direction, but it's spinning, maybe it's spinning along this axis as it moves in that direction, right? And as it moves, it's spinning along that axis. That's the curl. That's the curl vector. Yeah?
So it would have like a helix trail to it, basically?
No, because it's an infinitesimal point, right? So, I mean, if you give it any sort of like dimension, it's not going around something. Not like I think I understand. Like you're thinking it's moving like around point.
That way, it's curling at the same time.
I'm thinking of like a ball, like a baseball. Someone throws a baseball, it might be going like that, right? But the spin is doing something else. And if you had an axis through there, through that spin, that's your curl vector is the axis of rotation, and then the speed of the spin is the magnitude of that vector.
Oh, I was just going to say, isn't it like an axis then?
It's an axis. Yeah, it's an axis of rotation. So this animation, what it was doing, stopped doing, is that it's measuring the length. So I'm going to move this point to a different place. Right now we're computing the curl, the magnitude of the curl to be 1.5 something. So it's got some spin to it. But if I move to a different place, let me move to a different place. I'm going to move this around. See, now what happens, I'm at a different position. I'm at a different position, right? Do y'all see that the green vector got longer? So what should happen here when I press play is that I should be spinning faster. See how I'm spinning faster now? Spinning faster because the curl vector is longer. Make sense?
The green is the curl vector.
The green is the curl vector, which is the axis of rotation. The red is the direction that the ball or molecule is moving. This little disc is just to help you see the rotation, because if I didn't have that disc there, it would just look like lines spinning around lines. So if I turn this to the side and go like orthogonal to that, see now we're looking at that green vector is our curl vector, we're spinning around that. Or if I come into it from this side looking straight on, you know, something like this, it's hard to do, but you get the idea? You'll get this? So what made this hard to code up was making that disk move around and always stay going with the curl. Like I get the vectors to do whatever, but getting the disk to do that's harder to do. All right, let's think about curl in two-dimensional space. Instead of a three-dimensional vector field, two-dimensional. Sometimes it's easier for people to understand curl two-dimensionally. So think about a molecule. This is a molecule, and let's say this is a flow of water. Do you all agree that this molecule is going to be moving this way, right? Imagine that molecule had little like paddle wheels sticking out of it. Then the molecules on this side would be moving faster and pushing on the paddle wheels here, and then over on this side they'd be pushing on the paddle wheels here. And this looks pretty symmetric, doesn't it? So it looks like there's an equal push here and an equal push here. So do you think that this molecule is spinning at all as it moves down? No, it should just stay there. It's stagnant, right? As you can see, because well, is it not playing? It shouldn't spin, right? The curl is 0. Now, does anything happen if I move this molecule to the right? Should get what type of spin? Clockwise, counterclockwise? Should go clockwise. There we go, right? So now we're getting this. It's a net effect. These vectors are longer, right? It's a stronger force this way than these guys over here. These are smaller. So the net effect is that you're going to get some curl. I always like to just think of a little molecule just going down the river, and then these guys to the left are kind of doing this, and the guys to the right are pushing, but not as fast, and it's just kind of like going down the flow, right? Something like that. That's curl. What if we change what if we go the other side? I had something funny happen in my 13-14 today. You know, sometimes people will be like, hey, has anyone ever told you you look like so-and-so? You know, Student said, "Sir, has anyone ever told you that you look like Goofy?" I was like, whoa, okay, no, that's new. Now I feel goofy because I'm up here like dancing and spinning around, you know?
I'll never forget what curl is.
Yeah, look at the curl here. It's different, right? The rotation is different. Here it was clockwise, here it's counterclockwise, right? Makes sense from the vectors? Let's change the field. Look at this. This is a really weird field. It's hard to see visually right now that we have no spin. Let's move somewhere else. You think we're going to have spin if I move? Huh. Well, something is going on. We have no spin. We have no spin. So hold on a second. This is two-dimensional, right? So our vectors are in two-dimensional space. So the only way we could have curl is if we somehow extend these into three-dimensional space, right? Because curl requires a cross product. What do you think here? We're not getting any spin. It's a special field. What kind of field is this? It's conservative. Why? Because that last component of the curl, what's that last component? Zero.
So that equals 0.
So that means you have no vector going this way. Like the vector doesn't have an out towards us, does it? And if it's not out towards us, then it has to live here, so then it can't, the curl is 0. So if the curl is 0, you're conservative. That's the ultimate takeaway from this. But look at this right here. This is an example of a conservative vector field. Conservative vector fields, no matter where you go, you have no spin. So it's this like field where all the molecules are sitting there and none of them are spinning. No matter where you're standing, there's no spin. That's a conservative vector field.
Conservative vector fields have no curl.
Curl is 0. The curl is the 0 vector.
The molecule is still moving, right?
Yeah, they're still flowing, but they're not spinning as they flow. So this is basically what I just said. Curl creates an axis of rotation. The magnitude of the curl is the speed of the rotation. If the vector field is a velocity vector field of a fluid that's flowing, then the curl measures the tendency of the fluid to rotate or curl around a point. If the curl of 0, this is a typo. If the curl vector is the 0 vector, then there is no rotation and the field is called irrotational. Take a note, because on your next take-home, I'm going to ask you something about irrotational, and so this is what it means to be irrotational, is that your curl is the 0 vector. Now, if you're talking about a vector field in two-dimensional space, we can't do a cross product, right? Because you need three-dimensional vectors. But there's an easy fix. If we ever are given a field in two-dimensional space, all we have to do is extend that field to three-dimensional space by letting the z component function be 0. And then you can still compute curl. This is that big takeaway here. All right, we already saw earlier in this chapter that when the vector field is two-dimensional, the check for conservative is this check right here. These partials have to be equal, right? Now, we have a condition that will allow us to check for conservative vector fields in three-dimensional space, and that is if the curl of the vector field is the 0 vector, then F is a conservative vector field. I think that's a good place to stop, because divergence is next. And I'm going to be dancing again for divergence, so I want to save my energy.
I'll bring points next time.
Yeah. So we're down to what, 4 classes? We have 4 lectures left, all right? We have 4 lectures left, and we have, in terms of material, we have 3 sections, all right? We are going to get bogged down next week in 13.6, because this is it. We're going to do divergence, then we're done. 13.6 is going to take us all of next week. And that will leave us our last 2 days of class for 13.7 and 13.8. So it's going to be tight. We're going to just try and get to the finish line. I think we're going to make it. I want to be able to come in here and close the book. All right? That's my goal.
How often do you make it all the way through?
Every time. I've never not made it.
Let's make this your first.
Yeah. Let's make it the first. You want the divergence theorem. You want 13.8. The divergence theorem is nice. You do want it. Because if we don't get to divergence theorem, then the problems that you're going to have to do in the next section are going to just be hard. Because you won't have the divergence theorem.
This class is already.
Yeah. It's just a lot. I told you it was a lot of material, right?
Yeah.
Oh, I didn't lie, did I?